Okay, today we have to talk about 4.7 transformations of quadratic graphs. Okay, I apologize, I'm a little late. I actually left my iPad at home, so I had to run home to make this. And the noise you're hearing outside is my neighbor is having trees cut down. So, apologies all around, but here we go. It's not nothing crazy hard today. So, we're talking about transformations of quadratic graphs, and if you remember, we talked about a parent function earlier, and we said we had parent function, and in the case of quadratic, that was one of our parent functions. We had f of x was equal to x squared. We knew that that looked like this, where you had the parabola shape, and it passes through the 0, 0 point here as its vertex. Okay, and that's a parent function. And then we knew we could make new parabolas just by transforming it, shift it left and right, shift it up and down, do reflections, etc., etc. So let's remind you what each of those are real quick. So transformations review. If you had a function and it was x squared plus some number, then this would be the original parent function transformed by going a vertical shift up 3. So that's a vertical shift. X squared minus 5, if you had a function, would be a down 5. We could also shift things left and right if we change things inside the parent function. So inside the square in this case. So you can have something like x plus 1 and then square it. And remember, the x's were always backwards because you're looking for x minus something. So what is that something? It's a minus 1. So this is a left 1 shift, because left would be the negative direction, and x's are always backwards. And then we could do x minus 4 and have a right 4 shift. Some more transformations that we did before were reflections. So if we said that you had minus x squared, that would have been a vertical reflection. So of course, instead of opening up, it now opens down. Okay, vertical reflection. And we also did things with a number in the front. If you had a number bigger than 1, even 1.5, then you have a vertical stretch. And if you had a number that was less than 1, like 1/2, then we called it a vertical compression. Okay, so a compression is when things got wide or fatter, okay? And that's that. We could put these all together, like the next page. Okay, putting all the transformations together in one place and in a general format. Let's see, we could have a number in the front, and that number could be plus or minus. You could add or subtract something from x and then square it, or you can add or subtract something from the back end, right, which is basically adding it to y. So this is sort of a general format, and when we looked at that format, we always used to identify the vertex would be given by h comma k. How far did you move it to the left or right, and how far did you move it up and down? If you started at 0, 0, that becomes your vertex. So that was pretty straightforward. So as you can see, having a quadratic function that's in what we call a vertex form is very handy for finding the vertex, okay? So let's see if we can take any general or standard form of a quadratic and rewrite it so that it's now in vertex form. So this is going to be yet another way to find the vertex. Okay, so this time we want to go ahead and take this quadratic function. It's standard form, right? ax squared plus bx plus c. We're going to rewrite it in a vertex form. So what we're going to do is same thing we did before by completing the square, okay? Because right up here, this right here is a perfect square. So that's what we're looking for. So let's start this one by adding a box. So right here, the 6 doesn't help me make a perfect square, but I know something else will, so I'll put it there. And if I add a box to one side of the equation, and I need to subtract a box from the same side of the equation. Now, before when we were solving, we put things on both sides of the equation, but now we don't want to mess up the left-hand side. We want it to just stay as y, okay? So if I'm going to do something by adding a box, then I have to subtract a box from the same side. So I have plus box, minus box, and still plus 6. So other than that, it's really the same method. So think about what's going to go in the boxes. If I had, let me try and factor it, x plus 2 would be the factors to give me 4x in the middle, but that's going to give me a 4 here in the box, so that means I had to have a 4 here in that box as well. So these boxes become what is factored here, and then I still have to combine then these two numbers there. So what I have now is my function in vertex form. And I can easily see that the vertex is -2 and +2. And I'm done. So let's try another one. Okay, I want you to try this one. Again, we're going to try and write it in a vertex form. You'll need to remember to factor out the 2 from the first two terms only. You don't need to factor the 2 out of the 17. So give it a try, pause it, and I'll do it as well. Okay, so it's running through this. I remembered to factor out the 2. I remembered then I needed a 2 box when I subtracted it. So I get the vertex at 3, -1. Now, what can we do? We can go ahead and graph this function. Okay, so let's think about that. How will you go about graphing it? I can certainly put the vertex on at 3, -1, but that's all I've got so far. So, how are you going to find some other interesting points? Well, it certainly would be nice to have the zeros of the function. And let me show you what's a nice way to find the zeros of the function in a case like this. So finding the zeros, if you remember, is replacing y with 0, or if it had been written as f of x, you could have replaced f of x with 0. So 0 is equal to 2x minus 3 squared minus 1. So you have to solve that. Now, the nice thing about this is we can do the method where you take a square root of both sides, but the only thing they have to remember is it's going to be important to isolate the perfect square. So we have to get that by itself. So add 1 to both sides, and then we're going to have to divide both sides by 2. So I have 1/2 is equal to x minus 3 squared. So now I'm ready to take the square root of both sides, and I'm getting, don't forget your plus or minus, oh boy, 1 over the square root of 2, which I'll need to rationalize, is equal to x minus 3. So let me finish on the next page. Okay, so I got this far. I'm going to rationalize this 1 over the square root of 2 as the square root of 2 over 2 is equal to x. I'm going to add 3 to both sides, so I can put it there. So this is my solution. So these are my zeros. Now, you might want to get your calculators out. The square root of 2 is about 1.4. So the square root of 2 over 2 is about 0.7-ish. So I have 3 plus or minus 0.7, let's call it, is about x, because now I'm approximating. I no longer have an exact. If you ever see me ask on a quiz or test for exact values, you want to stay here. So this would be exact. And now I'm moving into approximating, so I can put it on a graph. So if I take 3 plus, I get 3.7 is about x, and the other x is about 3 minus 0.7, which is 2.3. So these are my two values for x-intercepts, because remember, those are the zeros of the function. So here I was with a vertex. Okay, so I went back and reminded myself my vertex was 3, -1, so I'm about here. I have my zeros at 3.7 and 2.3, so that's a good couple of points. Another point that might be fun to have is a y-intercept. So I could go back and get a y-intercept, of course, when x is equal to 0. Now in this case I have both forms of the equation, so it certainly would be easier in this case to go back to the standard form. But if you only had the vertex form, could you find the y-intercept? Yeah, of course you could still find the y-intercept. Just stick y in for 0. Or rather, just stick 0 in for x, you'll find the y, that's the y-intercept. Okay, so I need to remember what my original function was in vertex form. Okay, and so I'll put x equals 0 to find a y-intercept, and that finds for me negative 3 squared minus 1. You better be able to follow your order of operations here, right? Because I had a 0 minus 3, which is just a negative 3. Square it, I get 9. 2 times 9 is 18, and then y is equal to 17. So what's my y-intercept now? It's 0, 17. So somewhere up here. And since my axis of symmetry was here at x equal 3, then I know at 6, I've also got a 6, 17. Okay, and this was 0, 17. Alright, so there's my graph of the function when I connect this in a nice parabolic shape. Alright, so we can graph these things using just the vertex form. Certainly easier to find the vertex when it's in a vertex form. Okay, let's say they give you both the vertex and one other point. Could you write the equation of that parabola? So let's say they had a vertex that was negative 1, negative 2. And let's say they had another point that was negative 4 and 13. Okay? Remember, I'm giving you x and y pairs. But in the case of the vertex, I'm doing more than that. I'm giving you h and k. Okay? So right away, you're going to start with the function a x minus h squared plus k. Okay? So you really ought to memorize that and have that down pat. Okay? So then remember, that's our basic vertex form. And we're going to go ahead and put these values for h and k in. So now I have that f of x is equal to a x minus a negative 1, square it, plus a negative 2. So let's just clean that up a little bit. A x plus 1 squared minus 2. So here I have the function, and I know everything I need to know about it so far except for the a value. Okay? How am I going to find a? Well, I can find a because I know a second point here. Negative 4, 13 is an x and a y. So y takes the place of f of x, 13, is equal to, still don't know the a, but I know x is negative 4 plus 1 squared minus 2, and this will allow me to solve for a. So what do I have to do here? I have to add 2 to both sides. I have to work inside the parentheses and get a negative 3, square it, and get a 9. Okay? And then I'm going to divide both sides by 9. A is equal to 15 over 9. That allows me to rewrite this function as f of x is equal to 15 over 9, taking the place of a here. I still have x plus 1 squared minus 2. Okay? So that's the way I'm going to get an equation when you give me a vertex and a point. Alright, we'll cover the rest in class. Good luck.